NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
When even a Nobel Prize winner in physics starts to doubt our current understanding of the universe, you know that the astronomical hour has truly come. For decades, cosmologists repeated the same bedtime story, a narrative so comforting it felt etched into the very fabric of scientific thought. After the Big Bang, we were told, came a period of roughly 400 million years of cosmic darkness. Then, slowly, modestly, little galaxies flickered on, grew quietly, and only much, much later did they build the magnificent giant star cities we marvel at today. Nobel laureates signed off on this plot. Textbooks nodded along in agreement, and it became, for all intents and purposes, scientific dogma. But then, enter the James Webb Space Telescope. Its infrared eyes, with their unprecedented power, have now stared straight through those cosmic dark ages, and what it found is nothing short of astounding. Instead of the sleepy, sparsely populated village we expected, Webb revealed a bustling, crowded metropolis. This stark contradiction, these puzzling findings, are forcing even Nobel Prize winners to admit, perhaps with a sigh of exasperation, we might have to tear up the script entirely. Picture this. A telescope sends back an image of a galaxy so massive, so incredibly bright that, according to the standard model, it shouldn't even exist yet. It needs an extra 500 million years at least to reach such a state. Yet there it sits, a mere 300 million years after the Big Bang, fatter and brighter than our own Milky Way. One Nobel laureate, upon looking at this data, leaned back clearly at his wit's end and whispered, "That thing shouldn't be possible." Today, we're going to unpack 3 jaw-dropping revelations Webb has delivered from beyond the dark ages, explore why laureates are losing sleep over these universe breakers, and delve into how these discoveries could rewrite everything from star formation to the very nature of dark matter itself. Let's rewind a bit, back to that comfortable old story. The cosmic dark ages were meant to be a gentle ramp-up, a slow and steady progression. Hydrogen gas would gradually cool, gravity would pull wisps of it together, and then the very first stars, tiny, short-lived, almost shy, would ignite. Galaxies, we theorized, would build themselves bit by bit through a painstaking process of mergers, like adding Lego bricks one by one. Our most sophisticated computer models predicted that by 500 million years post-Big Bang, the biggest objects out there would be relatively puny, perhaps a few 100 million solar masses at most. But then, Webb's first deep-field image dropped a grenade right in the middle of that carefully constructed narrative. John Mather, a Nobel winner for mapping the cosmic microwave background, and crucially, JWST's founding father, couldn't hide his surprise. He remarked that the early census showed galaxies that were surprisingly big, bright, powerful, and numerous. We're talking about objects that already tip the scales at 10 billion solar masses, roughly a third of our own Milky Way's current stellar bulk, yet their light left when the universe was only 2% of its current age. The math doesn't just groan under this weight, it snaps. It means nothing other than that these gravitationally bound groups of stars already existed, fully formed, in an epoch where they simply should not have. Let's zoom in on these record breakers, these universe breakers as some experts have dubbed them. We're talking about galaxies like Glass Z12, CEERS 1749, and a whole swarm of other red smudges populating the early sky. They are emitting far more infrared light than should be available from the modest clumps of star-forming gas allowed by our conventional theories. Adam Rees, another Nobel laureate, this time for uncovering dark energy, put it bluntly, echoing a sentiment we've heard before: we have misunderstood the universe. The simplest fix, you might think, would be to just tweak our understanding of star formation efficiency. Maybe gas converted into stars at rates 10 times higher than anything we observe locally in the modern universe. But even that, while a tempting thought, stretches credulity. Another option is that the very first stellar generations were outrageously massive, perhaps up to 1,000 solar masses apiece, burning through their nuclear fuel like colossal rocket engines rather than gentle campfires. But even that might not be enough to explain the sheer scale and luminosity Webb is revealing. This is where the term universe breakers truly hits home. The 6 galaxies Webb added to our star maps in early 2023 were already much more massive than they should have been. Although these structures existed when the universe itself was only 500 to 700 million years old, they already reminded researchers of today's Milky Way. But as this is simply not possible according to conventional cosmology, these galaxies have truly earned their dramatic nickname. Instead of the expected baby galaxies, scientists saw impressive objects, all containing more than 10 billion solar masses of stars. One of them could even have a mass of over 100 billion solar masses. The question that now needs to be answered is, how was this even possible? Because if only one of these galaxies is real, it pushes our understanding of cosmology to its absolute limits. And it brings us to the real shockers: direct collapse black holes and dark stars. If you're enjoying this reality check on cosmic certainty, where the universe is constantly proving us wrong in the most spectacular ways, then do yourself a favor. Tap subscribe and ring the bell so you don't miss the next data drop. Trust me, there are more universe-bending stories headed your way.
Now, let's talk about something truly bizarre. Webb caught two disk galaxies mid-collision, their spiral arms warped into what looks like a perfect glowing infinity symbol. And here's the kicker. Right between them sits a supermassive black hole comfortably embedded in a glowing gas cocoon. Conventional wisdom, the bedtime story we were told, says that black holes grow from the tiny seed remnants of the first stars, slowly, patiently gorging on gas over eons. Yet this system's black hole already weighs in at hundreds of millions of solar masses, and it's far too early in cosmic history for that slow growth process to have yielded such a behemoth. This observation is not just a pretty picture, it's a profound clue. The favorite explanation, one that's been theorized for a while but lacked direct evidence, is direct collapse. Imagine a knot of primordial gas, so massive and so hot that instead of fragmenting into stars, which would then collapse into smaller black holes, it simply imploded in one go. A single, catastrophic event birthing a colossal black hole without any stellar middlemen. If such shortcuts were common, they would elegantly solve the long-standing puzzle of how quasars, those incredibly bright, distant objects powered by rapidly accreting supermassive black holes, existed just 700 million years after the Big Bang. Webb just delivered the first credible snapshot of that rapid pathway in action, offering a perfectly plausible explanation to a significant research dilemma. Now for something even weirder, something that sounds like it's straight out of science fiction. Catherine Fries and her collaborators noticed a few early galaxies whose infrared spectra peak in a way that ordinary starlight simply cannot explain. Their audacious proposal: dark stars. These hypothetical monsters wouldn't be powered by the familiar nuclear fusion that makes our sun shine, but by something far more exotic: dark matter annihilation in their cores. Picture this for a moment. A star 10 million times brighter than our sun, ballooned to the incredible size of Mars's orbit, shining courtesy of invisible particles smashing together and converting their mass into pure energy. Such objects could appear quickly, grow fat on the abundant dark matter in the early universe, and then, eventually, collapse into the supermassive black holes we observe later. Webb may have already bagged the first candidates for these cosmic cheats, with one even showing a helium absorption line that perfectly matches dark star models. If confirmed, this would be nothing short of revolutionary. It would provide a direct bridge between the esoteric world of particle physics and the grand scale of astrophysics, proving that the mysterious dark sector not only exists, but actively sculpted the visible universe from its very infancy. This is a discovery that would truly push our understanding of cosmology to its limits. So what are the Nobel laureates, the guardians of our cosmological understanding, saying about all this? John Mather, with his characteristic blend of wonder and scientific rigor, emphasizes that JWST's infrared range finally lets us witness the epoch of reionization firsthand. He fully expects decades of headaches as scientists grapple with reconciling this torrent of new data with existing theory. It's a sobering picture, truly. Adam Rees, on the other hand, stresses that the tension uncovered by Webb, the misunderstood universe he speaks of, goes hand in hand with another profound cosmic riddle, the Hubble constant discrepancy, or as it's often called, the Hubble tension. This is a major dispute among experts about how large the universe's expansion rate actually is, because previous measurements have produced completely contradictory values. In other words, the results we obtain depend on the measurement method used. One method, based on the cosmic microwave background, gives a value of around 67 kilometers per second per megaparsec. However, if we use local measurements, like those based on Cepheid variable stars, the expansion rate is suddenly 73 kilometers per second per megaparsec. The universe therefore appears to be expanding faster in our vicinity than in its entirety, and this should not really be the case.
And Rees agree. These discrepancies point to significant gaps in the standard lambda CDM model, our prevailing cosmological framework. Their bottom line is clear. Expect new physics, not just minor patches. The scientific community is now exploring everything from modified gravity on cosmological scales, a concept that has not yet achieved more than outsider status, but could explain discrepancies like the Hubble tension, to entirely new types of dark matter interactions. The next data releases from Webb could swing consensus, either toward a radical rewriting of our cosmic history or an elegant extension we haven't even imagined yet. The future will have to show to what extent these new approaches will be accepted and confirmed. Do these finds kill the Big Bang? No, not at all. Let's be clear on that. The fundamental pillars, cosmic expansion, the cosmic microwave background radiation, and the abundance of light elements still firmly anchor the idea of a hot, dense origin for our universe. What does die, however, is the tidy, predictable timeline we've grown accustomed to. Early structure may be less like a careful, methodical Lego build and more like a chaotic, exhilarating snowball fight. Rapid clumping, dramatic shortcuts, and unexpected formations. And that shift matters profoundly. Cosmology underpins our most crucial estimates, the behavior of dark energy, the ultimate fate of the universe, and even the likelihood of life forming in early epochs. Change the infancy story, and you ripple every downstream chapter, affecting our understanding of everything that came after. It's a truly tricky answer to a seemingly simple question. Stay with this incredible story as it continues to evolve. Hit like if you want updates when the next batch of Webb papers drops, and drop a comment telling us which mystery you'd bet gets solved first. Dark stars, direct collapse black holes, or those impossible universe-breaker galaxies. Your insights are part of this journey. The James Webb Space Telescope has, without a doubt, yanked us past the cosmic dark ages and slammed the brakes on scientific complacency. Massive galaxies appearing far too soon, black holes born in a single colossal gulp, stars powered by invisible matter. Each observation is like a love letter from the early universe, whispering, "You barely know me." Nobel laureates, once the guardians of the standard script, now readily admit that the plot needs a radical rewriting. The next discovery could arrive with tomorrow's data dump, shifting the paradigm again, pushing our understanding to its absolute limits. One thing is clear, absolutely certain. The cosmos is not a slow starter. It's a fireworks show that began earlier and burned brighter than we ever dared imagine. So keep watching, because if today's science is any clue, reality is far stranger and far more spectacular than yesterday's textbooks dared to print.